Well, hello, ladies and gentlemen. This is lecture number 2 for ME 2134. So let's go over the topics for today. Let's go over the topics. So we already went last time over the premise for the course, or the motivation for the course. So let's move on to some additional material today. We're going to look at units and dimensions. Units and dimensions. We're going to be looking at systems. And there are two different kinds of systems. There are closed and open systems, two different kinds of systems, open and closed. We're going to go over properties. We're going to go over properties. What's a property? What do properties signify? And there are various kinds of properties. There are extensive and intensive. Extensive and intensive properties, so two different kinds of properties. We're also going to be looking at, sticking with properties, we're going to be looking in particular at temperature, pressure, looking at temperature and pressure. And then we're going to finish off by looking at forms of energy. Forms of energy. Okay, so that's what we're going to cover today. Let's start off with units and dimensions. Oh, got to switch over here. There we go. Units and dimensions. Units and dimensions. So I'm going to define some dimensions here. A dimension is a generalized quantity. So dimensions are things like mass, force, time, length, degree. They are all the basic building blocks for how we describe or quantify properties of systems. So mass, I'm going to signify with an M. Force, I'm going to signify with an F. Length, I'm going to signify with an L. And time, I'm going to signify with a T. So those are the various dimensions. And of course, there's degree as well, like degree Fahrenheit or degree centigrade. If you want to put in degree there and put a little circle in the superscript, that's fine with me. But these are the main dimensions that we're going to be dealing with. I guess I'll put temperature here. Temperature, and I'm referring to degree, which I'm going to symbolize with a little circle, okay? Temp, which means degree, which means a little circle, okay? Okay, so let's make a little table here. I'm going to write out quantities, indicate their dimensions, and then indicate their units, both in English and metric. So, for example, length. length. So this has dimensions of L for length. And the English unit English, and unit metric, or SI. SI unit, English unit and SI unit. Let's see, for length, in English unit, it could be a foot. Foot, could be an inch, could be a yard, could be a mile, who knows? Foot, inch, yard. Metric, a meter's the big one, but it could be centimeter or it could be kilometer. Who knows? There are all sorts of things you can put in for units or metric. What about mass? So the dimension of mass is m. The dimension of mass is m. The English unit would be pounds mass. So LBM. LBM. Metric would be kilograms or a gram for the SI unit. Okay. Let's see here. What about force? Force, that has a dimension of F, or by the way. Let's see here, force is equal to a mass times acceleration. So F would actually be equal to a m times an acceleration, that'd be a length per unit time squared. So mLt squared, that's the dimension, resulting dimension for force, mLt squared. Okay? Unit on force for English could be a pound force, let's say. And of course, in SI units, we have newtons. So N or kilonewtons. Okay? What about pressure? Well, pressure is a force per unit area. So force over L squared. Or if you like, M L T squared L squared. The dash here means meter times a length, time squared times a length squared. That's what the dash means. It doesn't mean negative. It's just a dash, not negative. Units of pressure, well, in English, PSI, pounds per square inch, or kilo-PSI. And then, of course, we have pascals, or kilopascals in SI units. Okay? How about energy? How about energy? Well, the dimensions of energy are the same as that of work. Remember the energy balance? Work is equal to conservation of mechanical energy that we use to motivate our development of the full energy equation in the last lecture. Work is equal to a change in kinetic plus potential energy. That's the mechanical, conservation of mechanical energy. So energy or work, has to have units of, let's take the kinetic energy, 1/2 m velocity squared. So it has to have units of dimensions of mass times the velocity squared. So that would be length squared over time squared. Kinetic energy has units of mass times velocity squared, or dimensions ml squared over t squared. The unit for that in English is often the BTU, British thermal unit. That's the big one. That's the big one. Okay? And of course, the one in SI is joules. J for joules or kilojoules, whatever. Kilojoules. Could be kilojoules. What about power? What about power? Power is energy per unit time. Power equals energy E per unit time. So that would be a mass times the length squared over T, or time to the third power. Okay, so I'm just dividing energy by time. So I get mass length squared over time cubed. The big one, English, the big unit for power in English is the horsepower. Horsepower. And of course, the big one in metric or SI is watt. Watt. This is watt, not work. Watt, not work. Okay. That looks pretty good. Okay. Okay, so this is just a reminder of all the units you're going to be dealing with in addition to temperature. In addition to temperature, we're going to be dealing with in this course. You should bear in mind whenever you do a calculation to check the dimensions of your result. One good way to check your work is to make sure that the units or dimensions work out. If you get an answer and the unit is incorrect or the dimensions are incorrect, you probably made a mistake in the problem and the answer is incorrect numerically. So it's critical when you're doing thermodynamics to pay attention to units and dimensions. We'll deal with that as we do example problems. We'll go through and always carry the units with us when we do example problems, okay? Okay, let's move on to systems. What are systems? That's units and dimensions. What are systems? Well, there are two definitions of a system. In other words, there's a definition which includes two parts. Systems. What is a system? A system is a fixed amount of mass comma, or a fixed or a given location or region in space. A given region in space. A fixed amount of mass or a given region in space. Two different ways of characterizing two different systems. Let's look at the first part, a fixed amount or quantity of mass. A fixed quantity or amount a fixed quantity of mass. So what that looks like is we got a system here that surrounds a fixed quantity of mass m. Okay? So we've surrounded a mass m with a control volume. So here's our control volume. Control volume. And our m is our system. Our m is our system, okay? So our control volume surrounds a fixed amount or a fixed quantity of mass. We take a bit of mass, we dye it or color it, we draw a control volume around it. That is our system. This is called a closed system. No mass crosses the control volume. The mass inside stays inside. This is a closed system. So the first kind of system is a closed system, which is a fixed quantity of mass. No mass flows across the control volume or system boundary. No mass flows in or out of the system. It is a fixed quantity of mass. Fixed quantity of mass. What's the other kind of system? Well, that's the one about a, oops, did I switch the screen? I did not. Sorry about that. Okay. Systems. Sorry about that. I need to work on that. A fixed amount of mass or a given region in space. So the first kind of system is a closed system. We take some mass here and we draw a control volume around it. That defines our system, a fixed quantity of mass, referred to as a closed system. A fixed quantity of mass is a closed system, and the control volume surrounds the system, defines the system. What about the other definition? What about the other definition? The other half of the definition. A fixed region in space. What is that about? A fixed region in space. A fixed region in space. How about that? Fixed region in space. Well, let's say we have a some kind of a pipe or something, or a device, and it has mass flowing in, mass flow, and mass flowing out. Okay? I can define the region in space, which is my device. So here's my region in space. Okay, there's my region in space. Notice that mass is flowing across the system boundary. This dashed line is my control volume, or if you like, system boundary. System boundary or control volume. Notice that mass flows across the system boundary. This kind of a system where mass crosses the system boundary is referred to as an open system. Open system. Open system. Closed system. A specific fixed mass is surrounded by a control volume, and that defines our system. No mass crosses the system boundary. That's a closed system. If mass crosses the system boundary, and we have a fixed region in space that is our control volume, then that's referred to as an open system. Mass crosses system boundary for an open system. Mass does not cross the boundary for a closed system, okay? Big difference, big difference. If you are asking why this is important, it turns out that the conservation of energy, conservation of mass, conservation of momentum, conservation of entropy, all these conservation equations are different. They take a different form when you have an open system versus a closed system. Open system, we have mass crossing the system boundary. Closed system, we have no mass crossing the system boundary. Okay? In other words, the system is always the same fixed mass for a closed system. Okay? Two different kinds of systems. Two different kinds of systems. All right? Okay, let's go over properties. So we've talked about units and dimensions. We've talked about systems. Closed, mass does not flow across the system boundary. And open, mass does flow across the system boundary. Inlet, outlet. There could be multiple inlets and outlets. But the point is mass flows across the system boundary when you have an open system. Let's go over properties. Properties. What is a property? Well, to put it as simply as possible, a property is a characteristic of a system. Properties. Quote, a characteristic of a system. A characteristic of a system, something used to describe the system. Examples of properties. So example, temperature, pressure, volume, density, density rho. I suppose you could use a length, you could use an area, that would be weird, but let's stick with more thermodynamic stuff. You have energy, okay? And later on, we'll talk about it, you have entropy, S. S is entropy, not E. Okay, so these are all characteristics or properties of a system. All characteristics or properties of a system. There are two broad categories for properties of the system. Properties. There are two broad categories. There are extensive and intensive. Extensive and intensive properties. What's the difference between the two? Extensive properties depend on the size or scale of the system. Depend on size, or if you like, scale of system. And of course, intensive properties do not depend on the size. Don't depend on scale, size of system. Don't depend. Depend does not depend. Extensive properties depend on the extent or size of the system. Intensive properties do not. Let me give you some examples. Let me give you some examples of extensive and intensive properties. Extensive and intensive properties. Let's make a little list. Make a little list of extensive and intensive properties and how they are represented. Extensive. extensive props, intensive props, extensive props, intensive props. Well, the easiest one to do first is extensive. The first one that's pretty clear is extensive is the mass of the system. Mass M. The bigger the system is, the more extensive it is, the more mass it has by definition. So mass is definitely an extensive property. Definitely an extensive property. Volume. V, volume is extensive. The larger the system is, presumably the more volume it has. It has something to do with the scale of the system. Okay? Energy. E. Total energy, E. Okay? Kinetic energy. Kinetic energy, Ke. Remember, you got that mass times the velocity squared. The bigger a system gets, the more mass it has. So the bigger the system is, assuming velocity doesn't change, the more kinetic energy it has. So kinetic energy is extensive. Potential energy. Potential energy, PE. Okay. And internal energy, that's also, the bigger the system is, the more internal energy you have. Remember, internal energy was directly a function of temperature. The hotter something got, the more internal energy it had. The hotter something is, the more internal energy it has. It's energy that's related to the temperature of the system. So internal energy, running out of room, int energy, U, capital U, that is also an extensive property. All those things depend on the size of the system. Depend on the size of the system. Well, let's list some intensive properties. Basically, anything we can think of that we haven't listed as extensive is probably intensive. The big one is temperature. Temp. T, capital T. Yeah? Doesn't really matter how big the system is. Its temperature is a temperature. You could double the size of this room and the air temperature wouldn't change. Pressure is another one. Pressure P. Density. Why might density be intensive? Well, density is a mass divided by a volume. So the Greek letter rho, which is a mass divided by a volume. Mass and volume are both extensive, and therefore the dependency on the system scale cancels out. If you double the size of a system, you double its mass and you double its volume, and the doubling cancels out in the ratio. So density is intensive. It doesn't depend on the size or scale of the system. Specific volume. Specific volume. Lowercase v equals volume divided by mass. It's the inverse of density. Specific volume is 1 over density. It's volume divided by mass, not mass divided by volume. It's intensive for the same reason as density is intensive. The volume and mass change cancels out when you change the scale of the system, and you get a constant value for specific volume. How about some others? How about specific energy? Specific energy. When you hear the word specific, think whatever that quantity is, divide by mass. Specific energy. That's energy divided by mass. Here, let's spend a second on that to clarify so everybody's on the same page. Note, specific, whatever that is, equals divided by mass. Okay? Specific anything is that thing divided by mass. So specific energy is energy of the system divided by mass. What about specific kinetic energy? By the way, the symbol used for specific energy is E, lowercase e. E, which is capital E divided by mass. Okay? Specific kinetic energy. Specific kinetic energy. Well, that's going to be lowercase ke, which is equal to the kinetic energy of the system divided by the mass of the system. Lowercase ke. What about specific internal energy? Specific internal energy. That's going to be lowercase u, which is internal energy, uppercase U divided by m. Okay? See a pattern here? We can take any of these extensive properties divided by the mass of the system, and we get an intensive property with the word specific tacked onto it. You give me the energy of the system and the mass, I divide the energy by the mass, and I get specific energy, total energy of the system. E is the total energy, which is internal, kinetic, and potential. E is the total energy of the system. Divide it by mass, and you get lowercase e, or specific total energy. So this is one rule. Specific anything is that thing divided by mass. What's rule number 2? Extensive prop, which by the way is usually uppercase symbol, uppercase symbol, extensive property, an uppercase symbol, divided by mass gives you intensive prop in lowercase. lowercase. Intensive property in lowercase. Oops, sorry. So what's the second rule here? There we go. Second rule, first rule, note, specific anything is that thing divided by mass. You take an extensive property, which is represented in uppercase. You divide it by mass, that will give you specific that thing, and it's symbolized by a lowercase quantity, and therefore an intensive property. Uppercase divided by mass gives you a lowercase. Examples? Here they are. Volume divided by mass gives you lowercase v, specific volume. Total energy, E, divided by mass, gives you specific total energy, E, lowercase e. Specific kinetic energy and internal energy. They're all lower cases of the extensive symbol. So you give me an extensive property, I divide it by mass to get an intensive property on per unit mass basis, and everything becomes lowercase. Okay? So in this class, you're going to be coming across extensive properties like energy and pressure, energy, volume, entropy, and you're also going to be coming across a lot of intensive properties and a lot of specific quantities, which are intensive properties as well. Okay? All right, so we have intensive, extensive, and how to convert between the two. We got some nomenclature here. Usually the extensive properties, with the exception of mass m, are uppercase, and typically intensive properties, especially the specific quantities, are all lowercase. Density is a Greek letter, that doesn't count. Pressure and temperature are exceptions. Everything else is lowercase. Okay? All right. Now let's go over the two most common intensive properties and just spend just a little bit of time on them. We're going to look at pressure and temperature, spend a little bit more time on pressure. But we'll go over both pressure and temperature. So let's look at temperature. Temperature, T. Okay? Now clearly temperature is an intensive property, so it doesn't depend on the size or extent of the system. So let's remind ourselves, and I should remind you, what units are used to signify temperature. So we got temperature, which can be in degrees Fahrenheit or degrees Rankine. Rankine is absolute. In other words, in space, temperature in Rankine is approximately 0. 0 is the lowest temperature that a system can attain. Fahrenheit, Rankine, these are all English units. English units, all right? Rankine is an absolute. You can also signify temperature, obviously, in SI units. The big measurements for temperature there are centigrade C and Kelvin K, degree Kelvin, degree C. The absolute temperature, in other words, 0 in space, is Kelvin. Kelvin is absolute. I know I'm writing that. Absolute, okay? Space is almost 0 degrees, like a 2 or 3 degrees Kelvin. Basically 0, all right? And these are SI units. SI units. Metric, okay? How do we convert between the two? Well, I'm going to stick with the SI units mostly. Let's see here. To get temperature in, well, let's start with conversion between Fahrenheit and centigrade, and then we'll go on to centigrade to Kelvin. Temperature in degree Fahrenheit is equal to what? Temperature in degrees C times 9/5 plus 32 degrees, okay? You take the temperature in centigrade or Celsius, you multiply it by 9/5, and you add 32 degrees to it, and you get temperature in Fahrenheit, okay? I'll leave it to you to rewrite the formula for converting from Fahrenheit into Kelvin. I'm sorry, centigrade. Let's see, we also have conversion between centigrade and Kelvin. By the way, I presume you all know what the centigrade scale refers to. At 0 degrees C, we have freezing of water at atmospheric pressure at sea level. And at 100 degrees C, we have boiling of water at sea level, okay? So that's where the centigrade scale came from. 0 is freezing, 100 degrees is boiling of water at 1 atmosphere, okay? So let's see here, how do we get from the absolute, or I'm sorry, how do we get from centigrade to the absolute? So temperature in degrees centigrade is equal to temperature in degrees Kelvin minus 273 degrees. Okay? So you take the temperature in Kelvin, subtract 273 degrees from it, and you get temperature in centigrade. Okay? So these are results that you should have in mind. I will put a box around them, okay, so that you're keenly aware of them. You should be aware of this stuff, okay? You should be aware of this stuff. Let's move on to pressure. Let's talk a little bit more about pressure. We can say some stuff about pressure before we move on. I want to make sure we're all on the same page. All on the same page. What about pressure? So there are a couple of different kinds of pressure. I don't mean units, SI versus English. I mean how the pressures are referenced. Okay, how the pressures are referenced. Let's say we have a tank. Okay? So we have this tank, and on top of the tank is a pressure gauge. So there's our pressure gauge. We have some kind of a gas in here. Let's say. All right? Now, there are 3 relevant pressures for this situation. There's the pressure measured by the gauge. So I'm going to write down here, P sub G. P sub G equals gauge pressure. That's the reading on the gauge. Gauge pressure, P sub G. P sub G, gauge pressure. Gauge pressure. we've got the actual absolute pressure inside of the tank. So we have P ABS, P absolute, that is the absolute pressure. It's the pressure. Not as measured by a gauge, but the pressure. And then we have a pressure outside of the tank and outside of the gauge, out here in the environment. So I'm going to call this pressure out here P ref. P ref, reference pressure. P ref equals reference pressure. Reference pressure, P ref, reference pressure. Now, how are these all related? Well, the way an actual mechanical or any pressure gauge works is it measures a pressure difference. The pressure indicated on this gauge is the difference between the actual pressure inside of the tank, absolute pressure, and the reference pressure outside of the gauge. So gauge pressure is always a difference in pressure between the absolute. So P gauge is P absolute minus P ref. Gauge pressure is absolute minus P ref. Hopefully you've seen this in basic physics, okay? Gauge pressure, reference pressure, absolute pressure. By the way, what value does the reference pressure usually take? Not always, but usually. Usually the reference pressure is an atmosphere, the local atmospheric pressure. So when you measure the pressure gauge, measure the pressure inside of your tires using a pressure gauge. Let's say the pressure in the tires on your car or on your bicycle are 30 or 40 pounds, PSI, pounds per square inch. That's a gauge pressure. That is pressure above 1 atmosphere. So the pressure inside of your tire, if it says 40 PSI on your pressure gauge, is 40 PSI plus 1 atmosphere. An atmosphere is about 13 PSI, okay? So gauge pressure, P sub G, is absolute minus the reference pressure. Absolute minus the reference pressure, all right? And usually the reference pressure is 1 atmosphere. I'm not going to write that it is 1 atmosphere. I'm just going to say it. You may encounter a situation where the reference pressure is not an atmosphere. What if this tank is housed in a tank itself? What if there's a big tank out here and this little tank with its pressure gauge is inside a big tank and that big tank is already pressurized? Then your reference pressure wouldn't be 1 atmosphere, okay? Now, how do we measure pressures? Well, we can use a pressure gauge, which uses, so how do we actually measure pressure? We can use a pressure gauge, which using a spring and a diaphragm determines the force per unit area on some kind of internal part. And that gets translated into movement of the dial. The other way of measuring pressure is using what's called a manometer. Using a manometer. So let's say I have, so measuring, oops, that's not how you spell measuring. Measuring pressure. Well, clearly we can either use a pressure gauge. Okay, that's not very interesting. Pressure gauge, or if you like, transducer, or a pressure transducer. Pressure transducer. That's just a device that translates pressure into an electrical signal. Instead of a dial on a gauge, it transmits it into a voltage or a change in resistance. There's another way of determining pressure. It's very simple, using what's called a manometer. 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 Use a manometer. Or if you like, a column of fluid. Fluid column, okay? So what is this fluid column or manometer about? Let's say we have a tube, okay? Actually, no. Let's say we have a bent tube. A bent tube, a U-tube, if you like. Okay, so we have a tube. And this tube is filled with some kind of a liquid. So liquid in tube. Liquid in tube, all right? And this liquid has some sort of a density. Density, all right? Maybe it's water, maybe it's mercury, some kind of a liquid, who knows? Now, there is a pressure applied at this end of the tube. Okay, it's connected to some kind of a hose or a pipe or something. So I have a pressure P1 here, and I also have a pressure P2 right here, okay? Two pressures applied, one on the left and one on the right to this tube containing liquid. Now, let's say the levels of the liquid on the left and the right are as follows. Here's the level of the liquid on the right, and here is the level of the liquid on the left. Liquid level, there too. Okay, liquid level, all right? Now, this difference in height, this difference in height between the two liquid levels, I'm going to call this delta H. Delta H. It's a height, or you can call it delta H or an H. I guess we can call it H. H. Why not? Okay, why not? Doing a simple force balance on this manometer. It's called a U-tube manometer. A U-tube manometer. Simple force balance on the fluid column. Taking my fluid column system, taking the fluid as my system, doing a simple force balance in the y direction, I come up with a simple equation relating pressures and the height h. Delta P, which is equal to P1 minus P2. That's equal to the height h times the density of the fluid rho times the gravitational acceleration g. So rho is the fluid density, okay? And g is the gravitational constant or gravitational acceleration. Accel, Gravitational acceleration. Meters per second squared in metric, okay? Let's check the units on this equation. Let's check the dimensions and the units. If this equation is right, then the units on the left, which is pressure, should be equal to the units on the right. Give myself a little bit more room. Reference pressure, absolute pressure, gauge pressure, very good. All right. See, so for a U-tube manometer or a manometer in general, delta P, which is P1 minus P2, the way this is drawn, is equal to rho GH. Well, the pressure, of course, that has units of force over an area or pressure. See that squiggly line right there? I'm going to call that a tilde. Scales with or has dimensions of. Tilde, which means scales with or units of. Scales with or units of. Scales with or units of. Let's see, so pressure obviously scales or has units or dimensions of pressure, which is going to be a force over an area, which is going to be equal to a mass times a length over a time squared divided by a length squared. Mass times length divided by time squared gives me acceleration. Oh, I'm sorry. I forgot the mass. Yeah, oh no, there it is. Mass times length divided by time squared gives me a mass times acceleration. Okay. Let's have a look at the units of rho GH. Let's see, rho is mass per unit volume. So we have mass per length cubed. Mass per unit volume. Gravitational acceleration, that's going to be a length per time squared. And then we have height, h, which is a length. All right. Let me cancel out the length here with one of these lengths in the denominator of my density. I get mass over length squared if I do that. Let's write what I got. Mass times a length over time squared. So that's that, that's that, that's that, that's gone. Yeah, that's gone. Oops. And then I've got, I'm sorry, this one isn't done yet. Time, length, and mass are gone. And then I have in the denominator, length squared. That takes care of this term. Check. Okay? Mass times length over time squared divided by a length squared. Same as the units for pressure. Same thing. Units, same. Oh, whoa. Units are the same. The left-hand side of that equation has the same units as the right-hand side of the equation. So it is dimensionally correct. Okay? Dimensionally correct. Okay, I think we've talked enough about pressure here. We talked about gauge and absolute. We've talked about using a U-tube manometer or a manometer in general. In other words, the pressure difference associated with a column of fluid. Okay? let's take a moment here. I think I'm just about done. Yes. I'm going to talk just for a moment, one more minute, we're almost done, about energy, forms of energy. Forms of energy. Okay, let's talk about forms of energy, or the different kinds of energy. Different kinds of energy, all right? Forms of energy. Well, E is total energy. E equals total energy of a system. Let's say a given quantity of mass, all right? Now, E has many different ingredients. Total energy has many different ingredients. E is equal to, as we saw just in the previous lecture, it's equal to the internal energy, the kinetic energy, the potential energy, and there are other forms of energy. We'll talk about that in just a minute. Let's indicate what the source of these energies are, what they refer to. Kinetic energy, this has to do with the speed or velocity of the system. Velocity of system. Okay. So the faster the system is moving, the more kinetic energy it has. PE has to do with the system, the energy associated with the system's position. Usually under the influence of gravity. Position dependent. Position dependent. Okay? So there's position dependent. There's internal energy. Which is a function of temperature and a bunch of other stuff. Based on temp, T, and a bunch of other stuff. Okay? Now, what might some of this other stuff be? What might some of this other stuff be? So we have total energy. What might some of this other stuff be? I'm going to break internal energy into some individual parts. U. It's based on the temperature or how hot the system is and a bunch of other stuff. What is some of this other stuff? Well, let's see, how do I want to actually, yes. So internal energy is composed of the sum of a bunch of other kinds of energies. There's sensible energy, sensible E, sensible. Sensible energy is a function only of the temperature of the system. Function of temp only. Okay? Well, it's actually a function of mass because it's an uppercase, but let's forget about that for a moment. Sensible is a function, sensible internal energy is a function of the temperature of the system only. Then I've got plus, maybe make a little room. Plus, latent. Latent energy, latent energy. That's a function of the phase of the system. Is it liquid? Is it vapor? Is it a solid? So phase dependent. In other words, liquid or solid, forget temperature, nothing to do with temperature. Is the system a liquid? Is it a solid? Is it a gas? Who knows? Phase dependent. Then we have energy associated with chemical bonds. Chemical energy. Chemical energy, that doesn't look good. Chemical energy, that has to do with the chemistry. Okay? What's the chemical structure? What are some of the atomic bonds between the various molecules? So this is atomic bond, or I guess it's molecular bond energy. Molecular bond energy. Molecular bond energy. Okay? And then the other big one is atomic energy or nuclear energy. So there's plus atomic, or if you like, nuclear energy. Nuclear energy. Nuclear. Okay? And that's, of course, due to subatomic particles that make up the atom. Subatomic bonds. Bonds between protons and neutrons and electrons and all that, okay? Now, in this course, we're not going to focus, the reason I wrote it last is we're not going to at all look at atomic energy. If you're a nuclear physicist and you look at radioactive decay in fuels and nuclear reactors, you're very interested in this atomic energy term in the internal energy. Okay? We're going to focus on the sensible energy associated with internal energy, the energy associated only with temperature, how hot or cold the system is. The hotter the system, the more sensible internal energy it has. And the colder the system, the less sensible internal energy it has. We're also going to be looking on the latent energy component in internal energy. Is the system a liquid, a vapor, or a solid? That affects the temperature, that affects the energy. When you boil water, you're adding energy to it to change the phase from a liquid to a vapor. You're not heating up the water after it starts boiling. You're converting a liquid into a vapor by continually adding heat. Okay, so clearly sensible energy is, latent energy is very important. And then we have the chemical energy. That's going to come in the last couple of weeks of class where we talk about combustion and chemical reactions. Burning fuel in an oven, in a furnace or a combustion chamber, releasing heat, releasing energy. And we'll be talking about that in the last 2 weeks of the course. All right, ladies and gentlemen, I think we've gone long enough here. First lecture was just slightly short. This lecture is a little bit longer than I wanted it to be, but we're going to be moving on to chapter 2. We're going to be moving on to chapter 2 in the notes. Chapter 2 in the notes tomorrow, okay? Again, come by if you want to get a copy of the notes. So here it is right here. I don't know, 200 and 300 pages long, complete with all the tables you need, examples, And it very closely follows what we do in class. Very closely what follows what we do in class. Take care, ladies and gentlemen. We will talk some more next time.